When the rain falls and the snow melts, all of the resulting runoff moves through the local watershed, our environmental home. What happens to that water as it makes its way to our rivers and streams? That all depends on the characteristics of the local watershed. In an urban setting, the watershed has most likely seen considerable changes from its natural state. The flow of water in an urban drainage is very different from a less developed one. Major rivers or streams may be confined to narrow, straight banks. Smaller creeks and streams might be diverted into concrete-lined ditches or culverts. Wetlands might be drained and replaced with parking lots, buildings, or roads and highways. Woodlands and fields are few and far between, mostly paved over as well. All of these changes to the environment play a major role in how water moves through the urban watershed, and on its quality as it moves into the rivers, lakes, wetlands, and coastal areas downstream. A NOAA study in 2004 reveals that all of the built-up areas of the lower 48 states combined covers an area close to the size of Ohio, somewhere around 44,000 square miles. Considered on that scale, you can imagine the impacts that such enormous changes would have on the natural drainage system. What would happen in this supersized city after a warm, sunny day following a blizzard that leaves a foot of snow? Where would all that water go? Rain that falls on impervious, that is, impenetrable surfaces, such as roofs, parking lots, and streets, cannot infiltrate or sink into the soil and drain slowly into local waterways. Instead, it flows relatively quickly over the ground until it reaches a channel. The larger the area of an impervious surface, the more water collects in gutters, sidewalks, streets, and storm drains. This urban runoff is known as stormwater. Impervious surfaces aren't just concrete and asphalt streets and parking lots, but also buildings, sidewalks, and even lawns. Compacted soil, such as that found under many lawns built on top of construction debris, only allows for limited infiltration. With paved areas producing 5 to 16 times as much runoff than undeveloped meadow or woodland, water that would otherwise seep into the ground and help recharge the water table below is instead piped downstream. The net effect of this lost water is not the same in all settings, and its impact is only partly understood. One study conducted by American Rivers, the National Resource Defense Council, and Smart Growth America looked at metropolitan areas that experienced the most development in the past 20 years. They used various data sources to estimate the amount of water lost to runoff each year due to impervious surfaces. Though their figures are only estimates, they do provide a picture of how the built environment impacts water infiltration. Between 1982 and 1997, Atlanta's impervious surfaces annually flushed somewhere between 58 to 133 billion gallons of water downstream rather than allowing it to infiltrate the local water table. That's enough water to supply as many as 3.6 million people. Of course, a supercity the size of Ohio doesn't exist. But even broken up, all the paved and built-over areas that make up our local cities and towns create stormwater which has an impact on the local watershed. The impact on the water quality of the surface water and the local aquifer varies depending on the percentage of land coverage made up of impervious surfaces in a watershed. Research indicates that 10% impervious coverage can have a significant impact on most watersheds. More sensitive, semi-arid subbasins, such as Phoenix, will show irreversible impacts at 3 to 5% coverage. One of the major issues municipalities need to deal with when it comes to stormwater is pollution. Stormwater picks up pollutants on the ground along its path. This polluted runoff can have devastating impacts on downstream rivers, lakes, wetlands, and coastal waters. The Clean Water Act of 1972 set the stage for the EPA to regulate sources of pollution discharged into our waterways. In its early days, the Clean Water Act was very focused on point sources of pollution, such as industrial plants and sewage treatment facilities. And it has been very effective in cleaning up those sources of waterborne pollutants. Since the 1980s, the Act has been amended to also address pollution that isn't easy to pinpoint to a single source. This type of polluted runoff is often referred to as non-point source pollution. Polluted runoff comes from diffuse sources, such as pesticide and fertilizer from lawns and gardens, oil, coolants, rubber, and brake pad dust from cars, and salt and magnesium chloride from snow removal. Not all polluted runoff is necessarily considered man-made. The accumulation of tree pollen, leaves, lawn clippings, bacteria from pet waste in parks, sediment from construction sites, and other natural organic matter can also have a negative impact on downstream waterways by increasing nitrogen, phosphorus, bacteria, and turbidity levels. Nitrogen and phosphorus are chemical nutrients, the primary ingredients of fertilizer. When their levels increase, a process called eutrophication, it usually leads to increased plant, algae, and bacteria growth, which in turn leads to a decrease in available oxygen for native plant and animal species. In extreme cases, this process can throw an ecosystem like an estuary out of balance. Polluted runoff and eutrophication in this sensitive ecosystem can close beaches and harm or kill fish and shellfish. An additional impact from stormwater in some parts of the country is its temperature. As rain falls on hot, impervious surfaces, the runoff can become much warmer than the runoff on a comparable natural surface. Though water temperature isn't really considered pollution, it can have a similar impact on the biology of the watershed. Warm stormwater can induce growth of unwanted warm water plant and animal species and lead to excess bacterial growth. It's a major issue in the Pacific Northwest and other areas with valuable cold water fisheries. Every summer, the Chesapeake Bay, the largest estuary in the United States, shows the impacts of warm, nutrient-rich runoff. It's the cause of large dead zones, areas of low levels of dissolved oxygen, with negative impacts on the valuable commercial and recreational fisheries. Similar events happen annually in other coastal estuaries, such as the Gulf of Mexico off the Mississippi Delta. Another major concern with stormwater is the increase in volume and speed as it collects in the myriad storm drains and gutters heading downstream. The sudden increase in runoff can lead to urban flooding, and once the stormwater reaches creeks and rivers, to streambed erosion. Comparing a hydrograph, a graph of runoff volume versus time, in an urban watershed versus a watershed in its natural state, you can see that the potential for flooding is higher in an urban setting. The lack of infiltration due to impervious surfaces causes the stormwater to rapidly build in volume to a peak flow and then rapidly diminish. In areas with infiltration and more natural stream channels, the peak is less and it's spread out over time. The stormwater system in an urban area may be designed to handle the rapid buildup of water volume during a heavy precipitation event, but that water is all heading downstream, and the natural stream bed below will be affected by the increased volume and rate of the stormwater. Erosion and alterations to the stream banks and stream beds can lead to flooding and damage to nearby properties, while an increase in turbidity or cloudiness and sedimentation can harm aquatic life. If a municipality's storm drain system is connected to a sewage treatment plant, as it is in many older cities, a major precipitation event can quickly lead to stormwater loads that will overburden the system and cause sewer overflows. Such events can lead to sewer backups, known as combined sewer overflows, in homes and in waterways within the urban area, but also have impact downstream by contaminating fisheries and then closing downstream beaches. Let's take a closer look at some of the features of the urban landscape with the greatest impacts on stormwater flow. Rain that falls on city rooftops usually flows through gutters and downspouts to driveways and storm drains. For many homeowners, directing downspouts to a driveway lowers the risk of foundation or basement flooding. A house with a typical rooftop area of 2,000 square feet will produce around 1,000 gallons of water from a 1-inch rainstorm. A whole city of such houses produces rivers of water that can swamp stormwater systems. How homes are placed on lots also affects runoff. Many zoning codes require setbacks or minimum distances from the street or sidewalk to a house. Setbacks expand the amount of land needed to place development, increasing paved area and impervious surfaces. A Massachusetts Institute of Technology researcher found that 50% of the land is paved in typical residential subdivisions with 20-foot driveway setbacks. Though lawns are typically, but incorrectly viewed, as permeable landscapes, they are not. Scientists have found construction work frequently compacts the soil and limits its absorptive power. According to the Center for Watershed Protection, the bulk density of some lawns is similar to concrete. Roads and parking lots, on the other hand, are a well-known source of runoff. Street gutters quickly fill with water during storms and usually direct it to storm drains. From there, the water is directed into a local creek, a sewage treatment plant, or a retention pond. With the exception of retention ponds, very little of that water is retained for local infiltration. Instead, it heads downstream. Parking lots handle water like roads, and in addition are often bigger than they need to be. Cities may have formulas that calculate the required number of spots, and they may greatly overestimate what is needed. Olympia, Washington conducted a survey of parking space occupancy rates and found that over one-third of the spaces were not used. During times of peak parking demand, occupancy rates were less than 75%. A similar 2000 study by Purdue University of Tippecanoe County, Pennsylvania, found 3 public parking spots for each county resident. By their calculations, the parking lots generated a 25-fold increase in stormwater runoff and over 1,000 pounds of heavy metal runoff from parked cars. Parking lot landscaping can also compound the problem. City codes often require that landscaping be elevated at a minimum of 6 inches above the parking lot grade to provide a curbed tire stop. But such curbs prevent runoff from accessing and infiltrating the permeable grass and mulch in the landscape parts of the lots. Continued growth and development of our urban environment is inevitable. But there are ways to mitigate the impact of wet weather events on urban runoff, both in terms of reducing the amount of runoff and in lowering pollution levels. Mitigation efforts need to take place at the municipal level as well as in everyone's backyard. Many cities are adopting low-impact designs for municipal projects, amending zoning laws and ordinances, and putting educational efforts in place to raise awareness. Cities with combined sewer systems, those that combine stormwater and sewage, such as Chicago, Milwaukee, Pittsburgh, and Portland, have built or are building large retention systems to hold excess runoff during large precipitation events for later treatment. And in Chicago, a massive long-term project is underway to replace the nearly 2,000 miles of impermeable back-alley pavement with porous concrete. This effort will reduce runoff and relieve the load on the city's strained sewer system. Mitigation can start at a large or small scale. Every drop adds up.